Swayam Prabha. Digital India. Educated India.
Good morning. As we saw in the last lecture, the method of undetermined coefficients for solving the linear non-homogeneous ODEs is limited by the necessity of constant coefficients, and it can handle only a few selected functions as the right hand side, namely the polynomials, exponential function, sinusoids and their combinations. Now, for general situations in which the right hand side function can be anything, the input function can be anything, and the coefficients are also not required to be constants if they are functions, if they are variable coefficients, then the general method for solving the non-homogeneous differential equation is the method of variation of parameters. In this, we first note that if y1 and y2 are two linearly independent solutions of the corresponding homogeneous equations, then this combination, this linear combination with constant parameters C1 and C2 gives us the general solution of the homogeneous equation, that is the complementary function for the purpose of the non-homogeneous equations. Now, for the non-homogeneous equation, the solution needs to be linearly independent of these two basis members. Now, as long as these parameters are constant, we cannot have linearly independent function. So, what we try to think is that how about making these parameters as variables, that is as functions of x, and as we do that and we replace C1 and C2 by two functions u1 of x and u2 of x, then what we are doing? We are conducting a variation of parameters, and that is why this method is called variation of parameters. So, we consider variable parameters. So, we propose the particular solution of the non-homogeneous ordinary differential equation as u1 y1 plus u2 y2, and then we ask for the functions u1 and u2 that will make this yp satisfy the given differential equation. Now, one point is very clear, that we can take this yp and force it to satisfy the differential equation. That will mean that we will differentiate it twice and then take this yp and the resulting yp prime and yp double prime and insert in that equation, and we will say that this equation is now satisfied. But that will give us a single second order ODE in u1 and u2. Now, there are two unknown functions to be determined, and for that a single differential equation is not enough. We will need two differential equations to solve for two unknown functions. So, one more condition is needed to fix them. Now, at this stage we need one more condition between u1 and u2, apart from the condition that together they have to make yp satisfy the differential equation. Apart from that, we need one more condition, and we try to frame that additional condition in such a manner that our work is also reduced, our work is also made more easy. The way to do that is, at first, as we differentiate yp, this function, this proposed function, we get u1 prime y1 plus u1 y1 prime from the product rule. Similarly, from here u2 prime y2 plus u2 y2 prime. So, these are the four terms in the derivative of these two terms here. Now, we know that as we differentiate it further, then u1, u2, y1, y2, all four of them will generate their second derivatives, and that means that the resulting expression for yp double prime will have up to second derivatives of all the 4 functions y1, y2, u1, u2. With y1 and y2 there is no difficulty because they are known functions, but u1 and u2 when involve their second derivatives, that means that the resulting differential equation will be a second order differential equation. The additional condition that we need, we can choose in a particular manner which will obviate that second order. So what we do is that from here we collect the terms which has the first derivatives of the unknown functions u1 and u2. So that means this term and this term, and together we say that we will impose the condition on functions u1 and u2 that this term and this term together vanishes. That is, we impose this plus this equal to 0. If we do that, then yp prime reduces to the sum of the rest of the 2 terms, this. Now in this expression in yp prime we have got the derivatives of y1 and y2, but not the derivatives of the unknown functions. So that way when we now differentiate this, we get the derivatives of the unknown functions only up to first order. So that is this yp double prime. That again with the ordinary product rule will give us u1 prime y1 prime plus u1 y1 double prime, and similarly 2 terms from here, right. Now here again we find that the unknown functions u1 and u2 are involved only up to the first derivatives. Known functions y1 and y2 are involved up to second derivatives, but that is not a difficulty. Now on this, note that another condition like this we cannot impose, because if we impose another condition like this, that is if we try to say that these 2 together also vanish, then that will not make sense, because this condition and that condition together will imply that u1 prime and u2 prime are both 0, right, because these 2, this condition and this condition together will mean that we are looking for u1 prime u2 prime which satisfy a homogeneous system of linear equations with non-singular coefficient matrix. So that will give only the trivial 0 solution. So u1 prime u2 prime will become 0, which means that u1 and u2 will turn out to be constant, and that will not give us the solution of the non-homogeneous equation. So obviously only one condition we needed, and that we have got. The second condition we need to get by substituting this yp double prime, this yp prime, and this yp, this yp double prime, this yp prime, and this yp into the differential equation. As we do that, yp double prime, these 4 terms, plus p into yp prime plus q into yp is equal to rx. This is the given differential equation. Now as we rearrange these terms, collecting together all terms which have u1, that is, this is the first term, then from here we will get py1 prime, and then from here we will get qy1, right. So we collect the u1 terms together and u2 terms together. Now we know that y1 and y2 are solutions of the corresponding homogeneous equation. That means that this equal to 0, and similarly this equal to 0. So then cancelling these 2 0 terms, we get u1 prime y1 prime plus u2 prime y2 prime as equal to rx. Now this condition that we imposed, through which we also simplified the expression of yp prime, through which we avoided the second derivatives of u1 u2 in the resulting equation here, that is one equation, and the given differential equation gives us the second equation in 2 unknowns. The unknowns are u1 prime and u2 prime. Now this equation and this equation, if we write in the proper matrix vector form, then y1 y2, y1 prime y2 prime come in the coefficients, and we get the system of equation in the standard form. Now if we solve this, then we will get u1 prime and u2 prime, and we already know that this matrix is non-singular for all values of x under question in the interval for which we are looking for the solution. Now the determinant of this matrix is actually the Wronskian. So as long as y1 and y2 are linearly independent solutions forming the basis for the solutions of the homogeneous equation. So, we know that these are two linearly independent functions. So, this Wronskian will be non-zero. So, that means that the solution of this will give us unique u1 prime u2 prime. In other words, this is an invertible matrix. So, we get that solution. As we get that solution from the two equations here, we get u1 prime as this and u2 prime as this. Wronskian goes in the denominator, which is not a problem because it is non-zero. And then this is a known function of x. Similarly, this is another known function of x. So, direct integration will give us u1 and u2. These u1 and u2, when put in the proposed form of the particular solution, will give us the particular solution that we are looking for, that is u1 y1 plus u2 y2. Okay. So, this is the method of variation of parameters to find the solution of the non-homogeneous differential equation in a general situation. And the first step even in this is to find the solution, complete solution of the corresponding homogeneous equation. That is the first step, because they will form this matrix here. So, this is applicable for all functions px, qx and rx which are continuous and bounded, and it will be valid only for that interval in which these functions remain so. So, in this lesson these are the important points that we have studied. After looking at the function space perspective of linear ODEs, we studied these two methods, undetermined coefficients and variation of parameters. These same methods and the previous discussions on finding the solution of the corresponding homogeneous equation, all these now we generalize for higher order differential equations. So, first we consider this equation. This is the general linear ordinary differential equation of say nth order. So, up to the nth derivative is appearing linear, and these are coefficient functions which depend on x only. Now, understand again that we are here going to consider only those cases where p1, p2, p3 up to pn and r, these are functions of x which are continuous and bounded in the interval under discussion. Now, again for this we will have the general solution in this manner as yh plus yp, where yh is the complementary function. In other words, yh is the general solution of the corresponding homogeneous equation, that is this equal to 0. That is, it is a solution, it is the general solution of this equation. Now, for the homogeneous equation, suppose we have got n solutions, y1, y2, y3, etc. Then the state vectors of these solutions, when assembled as column vectors in a matrix, then what we have? See, it is an nth order differential equation. So, state vector will have the function itself, its first derivative, second derivative up to n minus 1th derivative. So, this is the state vector of the first solution. Similarly, this is the second state vector for this corresponding to this, and so on. So, when we assemble these as columns, then we get an n by n matrix of functions. That is, the first row is these functions, second row will have its first derivatives, third row will have the second derivatives, fourth row will have the third derivatives, and so on. The last row, the nth row, will have the n minus 1th derivatives of these functions. So, this is the fundamental matrix which will appear again and again. Now, first point is, what is the Wronskian in this case? So, the determinant of this matrix is the Wronskian in this case. This is a direct generalization of the case of second order differential equation. So, this is the Wronskian of all these solutions, all these n solutions. Now, parallel to the theory that we studied in the case of second order differential equations, here we will have corresponding points. First point is that if these n solutions of the homogeneous equation are linearly dependent, then the Wronskian will be 0. How do we prove that? We say that if these are linearly dependent, then for a non-zero vector k, we can find this. That is, we can have a linear combination of the n solutions 0, even though each contribution is not individually 0. That is, for a set of k's, k1, k2, k3 up to kn, not all 0 together, we can find a linear combination of these y's which turns out to be 0 if they are linearly dependent. And if so, that will mean that the derivative of this will give us sigma, that is sum of ki yi prime as 0, that is ki yi prime, that is j is equal to 1. The derivative of that will give us ki yi double prime equal to 0, that is for j equal to 2, and so on. That means up to n minus 1 we can construct these sums and get them 0 if the solutions are linearly dependent. Now note that this will mean, this and this together will mean that the fundamental matrix y into k is equal to 0, which means that its first row is this, second row is this for j equal to 1, third row of this matrix vector equation is this same thing for j equal to 2, and so on. So, the complete n rows we can construct like this, and note again that if y1 to yn are n linearly dependent solutions, then we can construct such a matrix vector equation, homogeneous equation, 0 on this side, and have a solution which is not 0, that is vector k is not 0. And that means that this coefficient matrix y must be singular, because for the homogeneous system of equation to have a non-trivial solution k, it is necessary that the coefficient matrix is singular. So, yx is singular, which means that its determinant, the Wronskian, is 0. So, this is the first point, that is the n solutions of the homogeneous equation being linearly dependent will imply that the Wronskian is 0. Now, if the Wronskian, now we try to show the converse. If the Wronskian is 0 at some point, then y, this matrix at that point, evaluated at that point, is 0, is singular, and then that will mean that a non-zero vector k can be found in its null space, which will in turn give this, which will imply that the solutions are linearly dependent. So, this is the converse of this. Now, together they also mean that 0 Wronskian at some point x0 will immediately imply 0 Wronskian everywhere, because 0 Wronskian at some point will mean that the solutions are linearly dependent, which in turn will mean that the Wronskian is 0 everywhere. This is x, and that will again mean that non-zero Wronskian at some point will ensure non-zero Wronskian everywhere, and the corresponding solutions as linearly independent. So, now what do we do with those linearly independent solutions if the Wronskian is non-zero? We say that with these n linearly independent solutions of the homogeneous equation, we have the general solution in this manner, as we had for the case of second order differential equation. And this linear combination, the complete solution of the homogeneous equation, will serve as the complementary function for the solution of the non-homogeneous equation. Now, we consider the first case of constant coefficients. Consider this constant coefficient case for homogeneous equation, for which the complete solution of homogeneous equation we can find. Okay. If the variable, if the coefficients are functions p1x, p2x, and so on, then in general we are not able, there are no analytical procedures to find out all solutions of this homogeneous equation. Now, in this case, if the coefficients are constant, then we can do that exactly as the second order case with necessary extensions and changes. Here also the left hand side of this equation has y, y prime, y double prime in linear combination. So, we expect solutions of this form, exponential solutions. So, if we take a trial solution of this kind and insert it, its derivatives, as many times we differentiate, that many lambdas get multiplied with it. So, we get the auxiliary equation as lambda to the power n plus a1 lambda to the power n minus 1 and so on till from here we get a n. Now, this is a polynomial equation of nth degree, that means it will have n solutions. So, out of from those n solutions, for every simple real root, that is if gamma is one solution of this polynomial equation appearing only once, that is in its factorization, if lambda minus gamma appears only once, that makes it a simple root. Okay. So, then corresponding to that, e to the power gamma x will be a solution. That is, for every simple real root, the corresponding exponential function will be a solution of this differential equation, because that is the idea with which this was started. For every pair of complex roots like this, mu plus minus I omega, you will say that e to the power mu plus minus I omega will be two solutions. Indeed, yes. And in the case of second order differential equation, we reorganized it and found the two solutions in a different manner. That was e to the power mu x into cosine omega x and e to the power mu x into sine omega x. So, these two will be the corresponding two linearly independent solutions of this homogeneous equation. Now, if we get a real root which is repeated, then if its multiplicity is r, then we will find that e to the power gamma x, x into e to the power gamma x, x square into e to the power gamma x and so on up to x to the power r minus 1 into e to the power gamma x, all these will give us r linearly independent solutions of this. This is something which you can prove, which you can show. Similarly, for every pair of complex roots which appears repeated, you will have similar additional linearly independent solutions. For example, if mu plus minus I omega appears twice, so that should account for 4 linearly independent solutions. So, first pair is e to the power mu x cosine omega x, e to the power mu x sine omega x, and the next pair will be these two multiplied with x. Similarly, if it appears thrice, the third pair will appear with x square e to the power mu x cosine omega x and x square e to the power mu x sine omega x and so on and so on. So, with multiplicity r, you will go up to x to the power r minus 1 power. Okay. So, this way, if you determine the solutions, n solutions of this polynomial equation, then from that you can determine n linearly independent solutions of this homogeneous differential equation. Now, after having the solutions in this manner, you want to find out the solution corresponding to the solution for the non homogeneous equation with this whole thing equal to sum r x. Now, if the equation is with constant coefficients like this and r x is one of those chosen functions for the right hand side, that is one of those special functions, polynomial, exponential, sinusoid or their mutual combinations, then the method of undetermined coefficients will give you a solution. That is for this. So, method of undetermined coefficients will work exactly as the extension of the second order case. Here also those things, those modification rules will apply, that is, even if this happens to be e to the power gamma x, but then if e to the power gamma x happens to be already there in the basis for solution of this, then rather than proposing e to the power gamma x, you will propose x into e to the power gamma x. Similarly, if e to the power gamma x, x e to the power gamma x and so on up to x to the power r minus 1 e to the power gamma x, up to this, if all of these are sitting already in the basis for the solution of this, then even if e to the power gamma x appears in the right hand side function, you will have to propose as yp x to the power r e to the power gamma x, that is the next into some constant and so on. So, this is a general rule. Now, So, method of undetermined coefficients is something which will work exactly as in the case of second order equation. And as you know that in the general case with general right hand side function and functions appearing in the place of coefficients a1, a2, a3, this will not be sufficient. For those purposes, for those situations, you will need the more general method, which is the method of variation of parameters, which will work in the general case, that is in this case, that will work in this case as well. So, for that, for solving that, we will consider a linear combination like this. Now, let us, so we propose a function of this kind, which is a linear combination of all these n functions y1 to yn, which are known to be the basis members of the corresponding solution of the homogeneous equation, the basis members of the solution of the corresponding homogeneous equation, that is the solutions of this. So, n linearly independent solutions of this equal to 0 is y1, y2, etc. So, yp is proposed like this. Now, we differentiate this and eventually we will differentiate it n times and insert all the functions and derivatives into this equation in order to find the solution, find a particular solution of the non homogeneous equation. Now, as we differentiate first time, we find that the derivative of these n terms will get us 2 n terms. In the first n terms, we will have ui prime yi and the other n terms will be ui yi prime. Now, we try to put additional condition that this is 0. So, when this part is 0, then the first derivative of this will turn out to be as ui yi prime. Now, this is 0 means basically that the rate of the function u is orthogonal to the vector function in the vector space sense, that is if u of x is a vector function with components u1, u2, etc., then u prime will be its derivative, its rate, and that rate is orthogonal to the vector function y of x. Okay. So, that is the condition we have imposed, and that gives us yp prime, which is like this. Now, note that this condition turns out to be the first row from this matrix vector equation, y1 into u1 prime plus y2 into u2 prime and so on, yn into un prime equal to 0. That is essentially this condition. Now, imposing this condition, we get the first derivative as this, which is free from u prime terms, which means that its derivative will be free from u double prime terms. So, we find out its derivative, and as we try to put its derivatives, in that there will be again 2 n terms together are taken as 0. That is the second condition that we have imposed. So, as we impose that from the derivative of this u prime y prime terms, the sum of those terms vanish. That is the condition we impose, and the rest of the 2 terms u into y double prime, that remain here. Now, this condition is equivalent to the second row, that is sigma yi prime ui prime, y1 prime into u1 prime plus y2 prime into u2 prime and so on is equal to 0. That is the second row in this matrix vector equation. Similarly, we go on differentiating the derivatives further. At every step, we go on imposing these conditions till the n minus 1s derivative that gets involved here, and corresponding n minus 1s derivative we get here, and this is the point, this is the stage where we have to find the last derivative that is needed, that is yn, yp n. So, when we differentiate this, we get the full derivative in which full 2 n terms come, ui prime yi n minus 1 plus ui into yn. So, these two both the terms will appear here in the nth derivative. So, note that from this point till this point there are n minus 1 conditions that have been imposed with the function, the first derivative, second derivative up to n minus 2th derivative. So, these are n minus 1 conditions that have been imposed. These are the top n minus 1 rows from here involving in the coefficients here up to the n minus 2th derivatives. The last equation we will get when we insert this ypn, this expression and all these expressions for the previous derivatives and the function itself also. So, when we put all of these expressions now into this differential equation given, then what we do? We add to this last equation p1 times this plus p2 times the previous one plus p3 times the still previous one and so on. Finally, p n minus 2 times this plus p n minus 1 times this plus p n times this, that is from here. As we do that and collect the terms together, then this term is here. Okay. This term is here u prime y n minus 1. Okay. And here the other terms, that is this into this plus p1 into this plus p2 into previous one and so on. So, there you will find that u is common in all these even up to this. So, in the that is why u has been ui has been kept common outside, and inside the bracket you have yi plus p1 into the yi n minus 1th derivative and plus p2 into yi n minus 2th derivative and so on, that is this actually. Now, we know that each of the functions y1, y2, y3, y4 etc. are solutions of the homogeneous equation, corresponding homogeneous equation, that is this equal to 0, and therefore, for every I separately this bracketed term vanishes. Okay. So, this whole thing goes to 0, this remains on the left hand side and Rx remains on the right hand side, and that is why we get this last row from this system of equations. And what is the matrix sitting here? This is our old friend, that is the fundamental matrix capital Y that we constructed from the state vectors of these n linearly independent solutions of the corresponding homogeneous equation. These are the columns. So, here is our fundamental matrix capital Y of x. So, this is the last equation and this is the assembled matrix vector equation together, y of x, this matrix into the vector u prime is equal to this vector with all zeros and Rx at the last entry. Okay. That can be said as En into Rx, which will mean that last one is 1 and here we have Rx, it is the same thing. So, this is the En, that is the last natural identity member in the n dimensional space. Okay. So, now this is the matrix vector equation in the rates u prime, and this matrix is non singular because these solutions form a basis, that means they are all linearly independent. So, this matrix is non singular as its Wronskian is non-zero. So, this non singular matrix can be inverted and this matrix vector equation can be solved. Now, usually I have told you earlier that in the context of linear algebra that the computation of inverse, numerical computation of inverse with the help of this formula is typically inefficient, but here we are doing the analysis in terms of not numbers, but in terms of expressions, and in this context this formula turns out to be of advantage. So, inverse of y is adjoint by determinant, right. So, if we use that, then the adjoint by determinant will come here and we can calculate u prime x. So, that is 1 by determinant into adjoint into this side. Now note that this adjoint matrix will be multiplied with a vector immediately which has all its entries 0 except the last one. Okay. So, from the adjoint only the last column is needed, that is adjoint y into En will essentially mean the last column of adjoint y. So, that means when we construct adjoint y, we do not construct the entire adjoint of this matrix, but we need to construct only the last column of it. So, last column of its adjoint will require the cofactors of only the last row, because adjoint will be the matrix formed by the cofactors of this matrix transposed. So, the last column of the adjoint will be formed by the cofactors of the last row. Okay. So, last column of the adjoint matrix is what we will need, that is adjoint into En. So, for that we will find out the cofactors of the elements from the last row only. Now, what is the cofactor of this entry? For the cofactor of this entry, we will need to remove this column and this row and whatever remains. For that, we have to find the determinant, and then we will put the sign according to the row number, column number of this, that is as which is the row number n and 1, 2, 3, that is the column number. So, that means the position of this will reflect in the sign, and other than that this column and this row will be removed. Okay. So, the cofactor of this element we can get by replacing this column with 0 0 0 0 0 0 1, okay, because this column anyway will be removed. So, if we put 1 here, then as we remove this row and this column, the rest of the determinant will give us the correct cofactor with the sign that we will get from the position. So, that means if we replace this third column with En, that is 0 0 0 0 1 here, then the determinant of this itself will be that cofactor, because in the determinant computation through this column we will get only one term, which is 1 into the rest of it, which is the correct minor, and the position we will get from the expression of the determinant anyway. So, that means that the entries, the first, second, third entry will be given as W1, W2, W3, when Wi is the same Wronskian, same determinant of this matrix when evaluated with En in place of the ith column. So, this gives us the expression for Ui prime. Okay. And then when we find that this is a function of x only, then we can evaluate Ui as direct quadrature, direct integration. And then this set of U1, U2, U3, U4 when inserted in the original proposal gives us a particular solution of this non-homogeneous equation. So, this is the way we develop the general solution for a non-homogeneous equation, that is we first develop the general solution of the corresponding homogeneous equation by replacing the r with 0. From that we find out the basis for all solutions of that homogeneous equation. That basis yn, y1 to yn we use to propose a solution of the non-homogeneous equation including the Rx